Hello and welcome. My name is Celeste Barnaby, and I'm a software engineer at Facebook. I'm part of a team called Big Code, where we do research in machine learning and build tools to improve developer productivity. Today I'm going to present a tool we developed called E.G, whose goal is to automatically generate API usage examples. I'm going to first talk about why we built this tool, then show you some examples of how it works. Then I'll go into the technical details and our evaluation. APIs are a pervasive component of modern software engineering. While writing code, developers often have questions about API usage, like how is this API typically used, and what other methods are commonly used with this one. To help answer these questions, developers often search for API documentation and usage examples. However, this can be especially challenging in companies where many APIs are proprietary. Because these proprietary APIs are only documented within the company by its engineers, there's no externally crowdsourced documentation or examples posted on sites like Stack Overflow. To address these concerns, we have designed a tool called E.G, which mines codebases and shows multiple common idiomatic usage patterns for API methods. E.G relieves the burden of manually curating examples for API methods, and automates the task of keeping API examples up to date and relevant as a codebase changes. Now I'll demonstrate how E.G works by showing you the code example E.G generates for 3 unique queries. Keep in mind that while we find E.G to be most useful for proprietary libraries with few handwritten examples, we cannot release such proprietary code for confidentiality reasons. I will instead show examples for some popular Python methods. This is the E.G example for the query os.makedirs. In each example, E.G emphasizes the code parts which are part of the common usage pattern in bold, while graying out the uncommon parts, which I'll refer to as filler. Further, E.G displays how many times each usage pattern appears in the repository. This example shows that it is idiomatic to first create an output directory with os.path.join, and then to call os.makedirs on the condition that the directory you are making does not already exist by checking os.path.exists. The second example shows an alternate idiom where os.path.dirname is called instead of os.path.join. And the third example calls os.path.isdir instead of os.path.exists. This is the first example for the query csv.writer. This example shows that it is idiomatic to open a file before calling csv.writer, pass a+ as the second argument to open, pass an empty string as the argument to the optional parameter new line, and call writer.writeRow after csv.writer. The second example for csv.writer shows an alternate idiom where a list of items is passed to writer.writeRow. And the third example shows an idiom where an argument is provided for the optional parameter delimiter. The third query we'll look at is json.dump. This example shows that it is idiomatic to open a file before calling json.dump, pass w as the second argument to open, and pass f as the second argument to json.dump. The second example shows that it is also idiomatic to pass an integer to the optional parameter indent. Finally, the third example shows that it is also idiomatic to pass true to the optional parameter sort keys. Now that we've seen a few code examples created by E.G, let's take a closer look at how E.G works. We formulate the problem as such. We have a large corpus of code and a query API method that we want to see examples for. In our experiments, we use a corpus of 1.9 million Python methods from open source GitHub projects. Our goal is to identify a short list of succinct code snippets representing common uses of the query API. The full details of the algorithm are in the paper, but here we will go through a few key ideas. The first phase of the algorithm involves finding a common usage pattern of the query API in our code corpus. Throughout the algorithm, we represent each method in our corpus as a simplified parse tree. We use this parse tree representation for two reasons. The first is that it consists of only program tokens, allowing it to be used uniformly across programming languages. So far, we have implemented E.G for Python and Hack. The second is that we can reconstruct the original code snippet with an in-order traversal of the parse tree. We'll see why this is important later. This is the high-level overview of this phase of the algorithm. We first search the codebase for all methods containing the query API method. Our goal in this phase is to identify a maximal subtree that both contains the query and is part of a meaningful portion of the parse trees in our list. We do this by first starting with a subtree consisting of just the query API method. For each parse tree in our list, we look at the adjacent nodes, meaning every node that is a parent or child of any node in the subtree. We identify the most common adjacent node and add it to the subtree. We then remove all parse trees not containing the most common node from our list. We repeat this process until the number of remaining parse trees goes below a certain threshold. Let's say half the number of parse trees we started with. To illustrate how this algorithm works, I'll go through a step-by-step example. Let's say we want to generate a common usage example for the built-in Python method split. These 6 code snippets are all the instances of split in our codebase. Keep in mind that this is an oversimplified example for illustrative purposes. To generate a good example, we would likely need more than 6 uses of the query in our corpus. We compute the parse tree for each code snippet. The goal is to identify a maximal subtree containing split that is found in at least half of these parse trees. To build our subtree, we start with the node corresponding to the call to split. Red highlighting indicates that the node is part of the subtree. We now look at all nodes adjacent to the subtree. In this case, these will just be the parent nodes of split. The adjacent nodes are highlighted in blue. We identify the most common adjacent node and add it to the subtree. Since the most common node is found in all parse trees, we do not remove any parse trees from our list. We now repeat the process of identifying adjacent nodes. This time, the most common adjacent node is not present in one of the parse trees. When we add this node to the subtree, we remove the parse tree that does not contain the node from our list. At this point, there are multiple adjacent nodes in every parse tree. We continue the process of identifying the most common adjacent node and adding it to the subtree several more times. We do this until we cannot add another adjacent node to the subtree without keeping at least half the original parse trees in our list. At this point, we are finished constructing our subtree. We have now created a parse tree representing a common usage pattern. The next step is to fill in the gaps in this parse tree. To illustrate why this is necessary, let's look at what happens if we try to create an example by doing an in-order traversal of the subtree we just created. As you can see, the example has a lot of gaps. There are some cases where a node was added to the parse tree, but not all of its children were. This makes it impossible to create a complete code snippet from this parse tree. So, what do we do? One option is to display the example like this, with the gaps left for the user to fill in. However, we have found that programmers feel more confident using complete code snippets. Thus, our goal in this phase of the algorithm is to complete the example by determining how to fill in the gaps in this subtree. To do this, we look at the list of parse trees we had at the end of the last phase. We will assign scores to each of these parse trees to determine which is most representative of a common usage of split. The scores are calculated by iterating over each gap in the subtree and adding points to each parse tree based on how common its filler for that gap is. For instance, for the first gap in the subtree, we add 2 points to the first and third parse trees, since their filler for this gap appears twice in the list. We add 1 point to the second tree, since its filler for this gap appears only once. We continue for each gap in the subtree. We then add up the points to determine which parse tree has the most representative filler. In this case, we find that the first parse tree has the highest score. We will use this parse tree to complete the usage example. Now, an in-order traversal of this tree creates a complete code snippet. The parts of the code snippet corresponding to nodes in the subtree are highlighted in bold, while the filler is left in gray. This highlighting indicates to the user which parts of the example are part of a common usage pattern and which parts are more unique. We also show the user how many code snippets this pattern is found in so they can understand how common the pattern is. I have just described how EG creates a single common usage example for an API method. However, in some cases, it may be useful to see examples of distinct common uses. EG creates multiple usage examples as follows. First, EG creates a usage example as described, maintaining a set of all nodes added to the pattern. EG then repeats the example generation algorithm with the same initial set of trees. If at any point the second most common adjacent node is not in the set of used nodes, and it has at least half as many occurrences as the most common adjacent node, we add that node to the pattern instead. We then continue the algorithm as normal. We repeat this process n times to create n distinct usage examples. I'll now discuss how we evaluated EG. In our evaluation, we aimed to answer the following 3 questions. I'll address these questions one at a time. To determine whether developers prefer EG code examples to code search results, we conducted a survey with Facebook developers. 18 developers participated in this survey. Each participant was offered a list of 6 common Python libraries and asked to select the 2 they were most familiar with. We showed the participants 10 methods in each library they selected, so 20 methods total. For each method, we displayed the top-ranked EG example and a randomly selected code snippet containing that method. The random example contained the line of code where the method was called, and 2 lines of code preceding and following the method call. This random example served as a reasonable stand-in for an arbitrary code search result, as code search engines typically display 2 to 4 lines of additional context by default. Participants were asked a series of questions about the EG examples and the code search results. We found that overall, participants preferred EG examples to random code search results 97% of the time. We also asked a few questions about the specific features of EG examples. 66% of participants said that it is helpful to see the number of examples that follow the same API usage pattern, and 100% of participants said that it is helpful to display common parts of the code example in bold. We next attempted to quantitatively measure how EG compares to similar tools. We compared EG against the same code search baseline described in the previous evaluation, as well as Program Creek, a website where users can query a Python library method and see functions from open source GitHub projects that call that method. Users vote on which functions represent the best example of a method. The top Program Creek example was taken to be the function with the most upvotes. To compare these tools, we used 4 popular Python libraries and selected for each library the 10 most used methods on GitHub. This gave us 40 methods total. For each method, we compared the top EG example, a random code search result, and the top voted Program Creek example, based on 3 metrics we defined to measure example quality. The first metric is succinctness. This is a measure of the number of lines of code in each example. We excluded empty lines and code comments. The second metric is relevancy. We measured relevancy by taking the ratio of relevant lines in an example to total lines. A relevant line is a line whose meaning and connection to the query method is clear without additional context. Relevant lines were determined by manually looking at the code examples. For instance, in the code example for np.array shown here, the first line does not show how or why reshape is called, so this line is deemed irrelevant. Without additional context, we also don't know what discretize.entropy MDL does, so lines 4 and 5 are not relevant. Since Program Creek examples are complete methods, relevancy was not a meaningful measurement. We only measured relevancy for code search and EG. The third metric is representativeness. Representativeness is measured by the ranking score that EG assigns to an example. Recall that this score is the sum of the number of occurrences of each filler option in the example. In this way, this score reflects how representative this example is of a common use of the query method. To measure the representativeness of the code search baseline, we first check whether the method containing this code search result is one of the methods containing the EG common usage pattern. If it is, we take that method's ranking score as the representativeness score. Otherwise, we assign the random example a representativeness score of 0. We were unable to compare Program Creek using this metric. Again, we only measured representativeness for code search and EG. These figures show the average length, relevancy, and representativeness for EG, code search, and Program Creek. Compared with examples from EG, code search results contained more irrelevant lines of code. We also observed that code search results were more likely to contain long, uninformative identifier names. Meanwhile, Program Creek examples were on average over 5 times longer than EG examples. Representativeness may be a less meaningful metric. However, this metric indicates a random code search result is unlikely to contain the top EG common usage pattern. Finally, we tested whether developers will incorporate EG into their workflows if it is made available to them. We did this by integrating EG into Facebook's internal code search website. When users query a method name in Hack or Python, the top EG example is displayed first, before the standard code search results. There is a link to the full contents of the file containing the code snippet used in the example, as well as a Show More Examples button that displays 2 additional common usage patterns. EG only shows the 3 most common usage patterns, ensuring that its interface is compact and easy to use. EG's integration into the code search platform was frictionless. Developers began to use EG with no prior announcement or tutorial. To measure whether developers use EG, we log each time a user copies or selects code from an EG example, clicks the file link, or clicks the Show More Examples button. Note that copying and selecting are the only events we log, with a clear signal that the user actually reused code in the example. Over a 24-day period, developers queried API methods that triggered EG examples a little over 1,100 times per day. EG received an average of 59 interactions per day, with 30 of these being copy or select interactions. While this appears to be a low ratio of interactions to total examples generated, there are several factors to keep in mind. First, developers do not always query method names because they want to see code examples. For instance, a developer may instead be looking for a specific file or class. We have no way to determine what a developer's intentions are when they query a method name. Additionally, because a central feature of EG examples is succinctness, developers may be learning or mentally copying from an example without physically interacting with it. Evaluating example generation is an interesting and complicated problem. A human study wherein developers complete short programming tasks could further illuminate how and to what degree EG helps developers to write code. A formal A/B test comparing EG against code search tools could also help to measure EG's effectiveness. Finally, more work could be done to ensure that EG does not perpetuate common anti-patterns. A potential solution would be to only index code in a codebase written after a certain threshold date. Exploring these options further is left for future work. This concludes my presentation. I'll leave you with a few key takeaway points regarding EG. Thank you for listening and have a great day.